Hi everyone, thank you so much for joining. Today we'll be diving into quantum computing. So now before we start, a little bit about ACE the Future. Our mission is to aim to create innovative opportunities for youth to explore emerging technologies and their impact on the world. So now here's an outline of what we'll be going through today.
Okay, starting off, just to define quantum computing quickly. So it's an area of computer science that develops technologies based on the principle of quantum theory and quantum physics. Um, the physicists, they use aspects of computer science, physics, and mathematics, and quantum mechanics to solve complex problems faster than regular computers can. On the side there, that's a photo of a quantum computer that belongs to IBM. Um, and they use the properties of quantum physics to store data and perform computations.
So now getting into what are qubits, they are the building blocks of quantum computers. So just like how regular computers have regular bits that they're made up of, quantum computers have qubits. So usually regular bits are two separate distinct configurations represented by a 0 or a 1, but qubits are cool because they can be both 0 and a 1, and this is called superposition. So we'll be talking more about that later in the presentation, but this is just a general overview. Regular bits can be compared to like flipping a coin, and you'll either get a head or a tail. So you'll get one or the other, aka the 0 or the 1. And a qubit is like a coin that's spinning, so it's both heads and tails at the same time. Also can be represented by a qubit, which is both 0 and 1. So there are two other important features of qubits called interference and entanglement that we'll dive into later. So after the qubits are in superposition, we can use interference to shift the probabilities in the qubit system, making the right answer more probable and the wrong answer less probable. And when qubits are entangled, whatever happens to one qubit instantly affects the other, no matter how far apart they are. They're really cool. So qubits have insane applications in AI and machine learning as they contribute to quantum computers, which are much faster computers that can process large data sets at once, just like how my colleague talked about before. So scientists are still figuring out all the amazing things qubits can do, but they're definitely an emerging technology to look out for. So diving more into superposition, superposition is the ability to exist in two places at a given time, as we talked about before. This phenomenon can be seen in quantum computers as it enables the qubits of a quantum computer to carry out multiple operations at once. This makes them more efficient than conventional computers. Let us assume that you want to search up something on the internet. A conventional computer would perform this command using multiple intensive steps. However, because the qubits of quantum computer can exist in two states, this command would simply be performed in a single step, making the overall operation speed much more faster and hence more efficient. And now we're going to talk about entanglement. So it is when a logical gate takes in one and then outputs more than one qubit. Then those two qubits become entangled. So this is a more technical definition. Entanglement is the term used to describe the ability of quantum particles to coordinate measurements with one another. Entangled is just a fancy word for saying one qubit state, when it gets measured, is going to be determined by a different qubit state when it gets measured. And in order to illustrate this, we're going to talk about the controlled knot or the C knot gate. And then I will come back to this fun little example. The C naught gate takes in two qubits. The first qubit can be whatever you want, and the second qubit can also be whatever you want. Then when it comes for the output, the second qubit gets flipped, only if the first qubit is 1.
Now diving into the math part of quantum computing. So as we mentioned earlier, quantum computing relies on quantum mechanics, which is a branch of physics with mathematical concepts like linear algebra, which is used to manipulate quantum states and operations, complex numbers, which are important for describing quantum states accurately, matrices and operators, quantum algorithms, And as you can see, an example is Shor's algorithm. And as you can see, it's like a really large number. And finding the prime factors of this huge number could take years with a classical computer, but only a few minutes or seconds with a quantum computer. And finally, probability and statistics. We use something called brat and cat notation instead of 0 and 1. It's like speaking the language of qubits, as you can see on the picture on the left. One qubit is represented as a two-dimensional vector. So the first one is state 0, as you can see on the image on the left. The second one is state 1, and the third one is a superposition. Now the reason for these square roots, you can see, is if we visualize the vector on a unit circle, the horizontal component is the square root of the probability of the qubit being in state 0, and the vertical component is the square root of the probability of it being in state 1. And the length of the vector is 1 because of the Pythagorean theorem. You can try that out yourself as well. And each point on the unit circle, as you can see, it represents a different quantum state. And a classical computer can only be 0 or 1, but in a quantum computer, it can be many different possibilities. And finally, quantum gates. These are like mathematical tools that help manipulate qubits. So the quantum NOT gate, or also known as the X gate, imagine you have a qubit that's like spinning a coin. Applying the X gate flips it. So if it was heads, then it would be tails, and then vice versa. And the Hadamard gate does something cool as well. It takes a qubit and puts it into a blend of both heads and tails. If that makes sense. Now, why is all of this so important? Where is it being used, and how is it impacting our world today? So, quantum computers have the potential to break traditional encryption methods, which could make our data more vulnerable to hackers. But however, quantum computers can also be the heroes here. Quantum cryptography makes it impossible to view data encoded in a quantum state without alerting the sender or receiver. So while quantum computers do have the power to shake up security, they also hold the key to making digital communication safer. Quantum computers can also process large data sets faster and improve pattern recognition, enhancing machine learning tasks in AI, which is also a rapidly advancing field with things like ChatGPT. And quantum computers can also model and simulate complex molecular interactions, accelerating drug discovery processes, and this can lead to faster development of new medicines and treatments, positively impacting the healthcare field. And finally, a cool fact is that in 2019, Google's 54 qubit processor performed a task in just 200 seconds, while it would have taken the world's fastest supercomputer 10,000 years. Now, here's a 2-minute recap video.
Even though we experience the benefits of classical computing every day, there are problems above a certain size and complexity that would take a traditional computer an impractical amount of time to solve. Enter quantum computing. All computers rely on a fundamental ability to store and manipulate information. Current computers manipulate individual bits, which store information as binary 0 and 1 states. For example, when our human eyes see the letter A, our computer sees a specific string of zeros and ones. From social media to spreadsheets, everything is done through these sequences of zeros and ones. Where current computers use bits, quantum computers use qubits. The bits in our current computers can only be either 1 or 0, but not both. But qubits can represent a 1 and a 0 at the same time. So if computers were coins, current models would be a coin flip, with either heads or tails as the only outcomes. But quantum computing would be like spinning the coin. The computer doesn't have to choose one or the other. This allows quantum computers to look at many different variables simultaneously. The good news is that quantum computers would be thousands of times faster than our current computers, possibly reducing the time to solve a complex problem from hundreds of thousands of years to mere seconds. The bad news? Quantum computers are very fragile and need to be perfectly isolated from heat and vibration. One quantum computer is kept cool at 0.015 Kelvin, or about 180 times colder than interstellar space. Although quantum computers promise to power exciting advances such as better batteries or new disease curing medicines, conventional computers will still be the easiest and most economical solution for tackling most problems.
Now, there's some links which I'll send in the chat for you to try out. These links have interactive courses if you're interested in learning more about quantum computing. Now, that's the end of our quantum computing presentation. If you would like, you could submit a blog or join us with the following links. And we have an upcoming webinar coming up called Passions and Pixels, where a computer science student at Stanford University will be speaking about her experiences. So if you would like to join, make sure to sign up with the link shown. And yeah, thank you so much for coming.